All right, we're going to pick up where we left off the other day. I was told that we definitely got through conjugate acid base pairs on what day were we here last? Yesterday, right? Yesterday. Okay, so that's about where we ended up. Now, did we get something in our notes yesterday about the difference between a strong acid and a strong base? Let's see where we, so that was the last page. So strong acid is going to have a very, very large K, and it's going to yield a weaker conjugate base than water. If you didn't add that to your notes, let's make sure you do that now. Notice the part that says yields a weak conjugate base. Make sure that you add weaker than water. That's going to come into play when we start calculating pH in a little while. Right, a weak acid.
Oh, wait, a weak acid.
A strong acid. Okay, so let's go back. Yeah, we're on strong. I'm just looking at strong. So a strong acid yields a weaker conjugate base than water. Than water. Mm-hmm. And then a weak acid gives a stronger conjugate base than water. So down here where you wrote this part in your notes, make sure that you just add in parentheses, stronger than water. Okay, because if it's stronger than water, that means that the pH is, if you had, say, a neutralization reaction and you're thinking, oh, the pH should be neutral, it should be 7. But if you've got a conjugate base that's in that solution, that's what's going to drive the pH. It's going to change things, okay? All right, so let's look at, I don't believe we looked at this screen. When we look at the difference between strong acids and strong bases, here you have your strong acid. Notice when you first start off, you don't have any water molecules involved. All you have is just the strong acid. As soon as you add it into water, immediately every single one of those ions, or every single one of those molecules rather, becomes an ion. So the hydrogen, the little blue atom right here, is going to drop off, and you have the anion that's going to drop off. So 100% right here on this little graph of your strong acid, and we symbolize that with the little letters HA, are going to become H positive and A minus. All of it, 100%. So yesterday we wrote down the strong acids, I hope, in our notebook. Did we do that? Okay, so let's see if you can remember those real quick. Caleb, name us one. HCl, very good. All right. Which one? It's right behind me. Okay, well, try not to peek over here. All right, let's see if we can get it without peeking. I'll try to block it. So HCl, what else, Tyler? HI, yes, Alex, sorry. HBr, okay. HNO3, all right, Javante. H2SO4, and the last one, oh, you said HClO4, and then the last one would be H2SO4. There you go. Okay, so also with our strong bases, they do the exact same thing. They're going to break apart into water 100%. But when we look at a weak acid, on the second side here, we have, this is showing you start off with a weak acid, and notice that only about, could you call that 10% down at the bottom? Maybe, maybe not. I mean, it looks like it's even less than 10%. It really depends on your weak acid. Notice that most of it is going to stay in the form of the H, and we'll call that the B because that would be your conjugate base, but most of it's going to stay in its original form, and you have very few ions present. Yes, Tyler? Yes, that's what happens when it hits water. Okay, so your second little diagram right here is what's going on when it hits water.
So, like, as I'm writing this down, I said on the other one, it all dissolved, but would I just say most of it stayed together on the weak acid? On the weak acid, yes, you can say most of it stayed together, okay, because that's actually what happens. The majority of it stays together. So that means that you've got very few hydrogen ions that are going to affect your pH, but that doesn't mean that your pH is necessarily going to be much different. You can have a weak acid that has an extremely low pH.
Okay, let's go back and let's make sure I talked about pH yesterday. So if you didn't have me as a teacher last year, I don't think you guys got to acid-base chemistry at all. Am I correct in saying that? No. Okay, so you might have. It's been a little bit since you had it. Okay, so what do you know about pH? What's the top end of the pH scale? 14. Very good, Tyler. All right. How about what's neutral? 7. 7 even. 7 even is neutral. Okay, so from 7.1 to 14, would that be an acid or a base? It's actually a base. Okay. All right. Yeah. So the higher the number, the more basic it is. Okay. And the lower the number, the more acidic. There you go. So just to kind of get that straight in your head. So we have from 0 to say 6.9, it's going to be an acid. All right. Okay. And we'll talk about exactly how that's measured in just a second. But just because you have a strong acid versus a weak acid doesn't mean you can't have a pH that's really, really low for a weak acid. The term weak comes from just how much they dissociate, or should I say a better term, ionize in water, because acids literally do change water into an ion. Remember what we looked at yesterday when we look at that, this equation right here. You've got the acid plus water. Here's your ion that changes. So you have the hydronium ion. And so we say acids ionize water. Okay. All right, let's go on through and let's talk about different ways to talk about acid strength. This is a good little chart just to make sure you have the difference in your head. A strong acid, I think we already wrote that down, that is going to have a huge Ka value. So its dissociation is going to lie to the products. Basically, what you're talking about here is you don't have any reactants left. It all pushed to the products. Okay, on the weak acid, you have your Ka is very, very small. So if you look at, maybe we wrote this down yesterday, the Ka is much, 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 much less than 1. Okay, and its equilibrium is going to lie far to the left. So basically, you have your reactants left. You don't have very many products. Your equilibrium concentration of your hydrogen ion when compared with the concentration of your original acid, if you look, these two things are just about equal. Okay, the little squiggly equal mark just means they're just about equal. And then over here with your weak acid, your hydrogen ion concentration, notice they've got a couple of less than signs in there. That just simply means it's much, much less than your original concentration. Okay, and then we've already written this part down. This is just summarizing everything. Your conjugate base is a much weaker base than water for a strong acid, and for your weak acid, your conjugate base is a much stronger base than water. Okay, so just a real quick summary chart. All right, let's talk about water real quickly. Now, water is a very unique species. Hopefully, you've learned that at some point throughout our time together. We know water is polar. Water has the most or the strongest intermolecular force of hydrogen bonding. Now, the interesting thing, though, about water is based on our definitions from yesterday, the Brunstad-Lowry definition, water can behave as either an acid or a base. It can either donate a hydrogen or it can receive a hydrogen. Okay, let me show you what I'm talking about with that. Sorry, let's see if I can get to some white space here. Okay, so if we have water, water can join up with another water molecule. And if you have one water molecule that happens to have a lot of kinetic energy and it's just really, really, it's got a lot of, movement, it can rip one of the water molecules apart. Okay, remember that each water molecule has a lone pair of electrons or two lone pairs of electrons there. And so the breakage point would happen here if you've got one other water molecule that has a lot of energy, and it gets so much energy that that attraction between the lone pairs of electrons and hydrogen becomes so much, it can rip that hydrogen off of there. And so whenever it does that, you end up with the hydronium ion. So if that one rips off that hydrogen, you have a hydronium ion, and then the leftover piece, this part, is very good, Javante, the OH negative, the hydroxide ion. And so you see how water can behave as either an acid or a base. one of those water molecules was behaving as an acid, it donated a hydrogen. So that would mean this one that donated the hydrogen ion was acting as the acid. The one that took the hydrogen ion was acting as a Brunstad-Lowry base. Okay? And so over here now we have, if this one was the acid, it donated the hydrogen. Remember, it becomes the conjugate base. And the one that took the hydrogen, which was originally the base, becomes the conjugate. There you go, the conjugate acid. Okay? So one water molecule acted as the acid, the other one acted as the base. And that's what we call that term amphoteric. So let's get back to our definitions here real quickly. Okay, so water is an amphoteric species. It behaves as either an acid or a base. Okay, now one thing that we know, and this is at this specific temperature, 25 degrees Celsius, probably very close to 25 degrees Celsius in here right now, maybe actually a little cooler. You could go get a thermometer out and measure it and see how warm it is. But at 25 degrees Celsius, the combination, when you multiply the hydronium ion concentration and the hydroxide ion concentration, you get this value. Now, one thing that I think we need to get before we go there is how exactly did they come up with that number, okay? So let me go over here and let me show you something that's happening. In any sample of water, and so from this point forward, if you drink some pure distilled water, one thing you need to realize is you're not drinking just H2O. You're actually drinking some hydronium and some hydroxide ions. You got both things going on there. Now, how many water molecules actually do this? Well, at 25 degrees Celsius, there are about 2 in 1 billion that will undergo this. It's called an auto-ionization process or self-ionization, okay? 2 in a billion. You're like, oh, that's really not that much, 2 in a billion. But when you think about how many water molecules there are in just a drop of water, that's actually quite a few. And we find, or chemists have found, that the concentration of 2 in a billion is 1 times 10 to the negative 7th molarity, okay? So if you've got 1 times 10 to the negative 7th molarity of the hydronium, what would your concentration of the hydroxide ion be? There you go, 1 times 10 to the negative 7th. Okay, and since this reaction, and I should have shown it a better way, is really an equilibrium reaction, then we could write a K expression for that reaction. Remember that water is a pure liquid, but once you have these ions, these are aqueous, okay? And so if we write our K expression, this is what it's going to look like. K equals the hydronium ion times the hydroxide ion, just like that. And we call this K, it's a special K, we call this K the KW, all right? So far we've learned K, I may have attached to KC, right? KP, that's different, that's a different K. KQ, maybe you've seen that. KSP, we've had that one. Okay, so now we have KW, and we're also going to be talking about Ka for acids and Kb for bases. Okay, all the Ks are the same thing. They're all based on concentration, except for that magic one. Which one is so different than the rest of them? I just said it a few minutes ago. Not KW. The one that's based on pressure. KP, because remember we had that equation to transfer from KC to KP. All these other Ks that I'm giving you, these are all KCs, okay? They're all based on concentration. So KW is just, it's based on the concentration of the hydronium and the hydroxide ions. So when you multiply those two numbers together, the 1.0 times 10 to the negative 7 times 1.0 times 10 to the negative 7, then notice what you get. You get that magic number, 1.0 times 10 to the negative 14, okay? Now, you guys told me something a few minutes ago. What is the top end of your pH scale? 14. it is not coincidental that the KW value has a negative 14 there. Okay, yes, ma'am.
That's the higher.
Yes, that's the highest. Yes.
That different than what you just did on the other one?
No, it's basically here. It's the same thing. So I did hydronium times hydroxide. And why do they have H plus? That's a good. Is that what you're asking about? Okay, so H plus and the hydronium ion can be written interchangeably. They mean the same thing. I will tell you that your chemistry professor in college may just adamantly say you must write it as hydronium. Okay, but AP is cool with you doing it as H plus. So we're fine. You can write it either way. Just understand it means the same thing. Okay. Thank you for pointing that out. All right. So when we multiply these two things together, we get 1.0 times 10 to the negative 14th. No matter what the solution contains, the product of those two things multiplied together always are going to equal that number. Okay. Always. So at 25 degrees Celsius, we have to be really careful with that. So if the temperature changes, your KW would actually change. Remember, that's the only thing that can change K. So if we have it at a different temperature, then our K value is going to change. Yes, sir.
So H plus and O2 like together equal that, or just one of them?
Whenever you multiply them together, they equal that number. Yeah. So the combination, the product of the hydrogen ion and the hydroxide ion are always going to equal 1.0 times 10 to the negative 14th at 25 degrees Celsius. So that's like it's a constant, okay, that thinking you might need to stick in your brain. All right, that one's just one that it's gonna help us to determine, like, if we know one of these and we know this number, then we can figure out the other one. All right, so let's continue on with this line of thinking. Now, let's talk a little bit about what would happen as long as you have the hydronium ion, and I'm calling this the hydronium ion. As long as you have that, H plus is equal to OH minus, you have a neutral solution, okay? And I probably should do this for the people who are watching this later because I don't think they can see my mouse. So let me see if I can draw on this. Okay, so what I was talking about on this one, the hydronium ion, okay, as long as it's equal to the hydroxide ion, the solution will be neutral. Okay, whenever your hydronium ion concentration is greater than the hydroxide ion concentration, you have an acidic solution. Okay, that makes sense. And the other way around, when you have the hydroxide ion concentration is greater than the hydronium ion concentration, then your solution is going to be a basic solution. Okay. All right, with me, Caleb? All right, let's see what else we might need to add to our. Let's erase that. I could just erase it, but all right. Can I go back? You bet. There you go. Sorry. Okay, so what makes an acid solution? Let's just kind of review real quick. What do you have to have more of to have an acid solution?
Oh, yeah, you have more of the acid.
The acid part, right, which is the H plus. Good. Okay, and to have a basic solution, you have to have more of the base part, which is the OH minus. Okay, that makes sense. All right, if they're equal, it's neutral. I'm not sure. I don't think I can play this video, so let's move on through. Okay, so let's just look at any general acid being added to water. Okay, and notice we've got our acid. A general acid is HA or Ha, and A would mean your anion. That's what that's standing for. Okay, and then it's just any random chemical, whatever your anion is. Okay, all right, and then we've got water is acting as our base, and notice the acid loses its hydrogen ion to the base. So the hydrogen ion is coming off here. It's joining up with the water molecule. It becomes the hydronium ion. That's what the base becomes. So the base is then the conjugate acid. And because this lost the hydrogen ion and it is now here, okay, so HA became that species, it is the conjugate base. Okay, now let's take all that information and we're going to look at an equilibrium constant expression for an acid acting in water. Okay, so the next thing that we've got right here is, what does this look like? And all we're doing is we're just writing the expression for what we have. Notice which part is not in our equilibrium expression. We have the hydronium, we have the anion, the water's not in there. And why, again, just to refresh our memory, why would water not be written in? Because it's amphoteric? That's a good guess, but no. Look at its state symbol, guys. It's a liquid. So remember, two things can't go into your equilibrium expression. Liquids and solids. That's right. So gases and AQ go in, but not liquid and solid. So here's your Ka, and we would actually call that a Ka if you want to write that down real quick. That's what you're always going to be writing when you're dealing with an acid. So Ka equals the hydronium multiplied times your anion divided by your Ha, your acid. And guys, to be quite honest with you, this is on your equation sheet. I'm going to show this to you as soon as you get that written down. So if you're like, oh my gosh, I forgot. I mean, which we shouldn't, because it's just an equilibrium expression, products over reactants. But if you needed a refresher or something to kind of kick in, let me show you. Right here on your equilibrium part, it is written, already done for you. Okay? It's just in the general format, but it's there. You also have like how you would write a K expression. It's products over reactants taken to the powers of their coefficients. They're showing you that example there. So there's really no reason for you to forget how to write a K expression, okay? Do not put pluses in there. I think I was, if anybody did put pluses, I was like, what is this? What are you doing? So it's to make a point, because I don't want you to like mess up, because you've got so many helps on your equation sheet for you not to miss it. Also, look, KP has an example there of how to do KP on your equation sheet. Now, if you see, so far we've talked about Ka. We will talk about Kb. It's also on your equation sheet. Today we've talked about Kw, and look, if you don't want to memorize that number, it's right there on your equation sheet, 1.0 times 10 to the negative 14. So use your equation sheet to help you when you're taking tests, okay? And then today we're going to jump right into this part right here. You've got, how do you find pH? pH is actually taking the negative log of your hydrogen ion concentration, okay? So there's some pH formulas there that we're going to find helpful. So let's go on to that. But first, let's do this little quick concept check, okay? If the equilibrium lies to the right, and since I don't have this on my PowerPoint mode, the answer is down there underneath it. If the equilibrium lies to the right, the value for the Ka is very, very large, or greater than 1. If it lies to the left, the Ka is going to be very, very small, or less than 1, okay? All right, let's move on past this since all the answers are on there. Okay, so yeah, we're gonna skip this. I can't show y'all all this without throwing up the answers here. So let's do this real quick. Instead of us having all these answers in here, let's go to our lecture guide, okay, and let's do some dissociation equations to help us out. Get this out of the way. There we go. Okay. All right, so sample exercise 1 says, write the simple dissociation or the ionization reaction. Caleb, you with us? Okay, this is wakey time. Caleb. Okay, all right. Omitting water for each of the following acids. So all we're going to do here, guys, is we're just simply going to break these apart, okay? Don't show water. So we have HCl, and what are we going to break that into? H positive and Cl negative. Very good. Okay. All right, acetic acid. I feel like we did this one yesterday on the board, but what are we breaking that one into? Good. Okay, NH4, if we're, this is acting, actually it would be acting as an acid because it's got an extra H. All we're doing is we're breaking that H off. And what's left over? NH3. No charge because it was positive and now it's becoming neutral, okay, because you took off a positive one. So just kind of think of, imagine a number line. You're only removing one positive. All right, the next one, where is the hydrogen? We've got a couple places hydrogens could come off. Very good. It's going to come off this NH3 part. Good job. So we have C6H5 NH2 plus the hydrogen ion. I kind of wrote that one backwards, but it doesn't matter. All right, and then on this one, we've got to get a hydrogen out of there, right? Okay, but just one hydrogen is going to come out of that. So we're going to get a hydrogen off, and then our species is going to be like this. I've got to remember how to write this. This is a complex ion, but we've got aluminum. And so if one hydrogen comes off of one of those water molecules that's actually attached to the aluminum ion, then we have an OH, right? Okay, so this will be aluminum hydroxide, just with an OH there. And then water, but we reduced our water down to how many now? 5, that's right. So one of these water molecules that was in here, it broke apart. Okay, and remember how water breaks apart. It breaks apart right there. So this is the hydrogen that came out of that. And then we have 5 water molecules left. Now let's do our charge. If we originally were at 3+, what's our overall charge going to be now? 2+. Very good. Okay. So that's how you do one of those. I feel like we should be able to see this a little bit better. Is that helping? I don't think it's helping. All right. Okay, let's look at that next exercise. Okay, so this is actually what your concept check was asking you to do. So we're going to use table 14.2 to arrange the following species according to their strengths as bases. So bases. Now, here's the concept we need to remember. Okay, strong acids produce conjugates that are stronger or weaker than water. You guys wrote this down a few minutes ago. So strong acids produce conjugate acids that are weaker than water. Weak acids produce conjugates that are stronger than water. Okay, so what we need to do is we need to figure out if these species come from a strong or a weak acid. Okay, so if I put an H on front of this, is HF one of our strongs? No, so it comes from a weak acid. Okay, is HCl, is that one of our strong? Okay, so I'm just going to write strong behind it because it comes from a strong acid. How about HNO2, strong or weak? Weak, okay. And HCN, strong or weak? Weak. See, if you know all your strongs, then everything else is weak. Okay, now, strong bases make conjugates that are weaker than water. So we've got one that is weaker than water, right? Okay, so it says arrange the following species according to their strengths as bases. So the strongest one, are we going to go, what do y'all want to do? You want to go from, you want to go weak to strong. Okay, so our weakest one is going to be Cl minus. Okay, so Cl minus is going to be weaker, I should do it like that, right, than water. And the rest of these are going to be stronger than water. Okay, but we've got to put them in order. So we're going to go to table 14.2, and if you flip your paper over, you can find table 14.2. All right, what you've got to look at is you're looking at the value of your Ka to determine how strong your acid is. Okay, remember, the bigger the Ka value, the stronger it is, which would make a weaker conjugate. So you said, let's find them on here. You got HF, HNO3. What was our other one? HCN. Okay, so which one is actually the weakest acid? HCN. So it would have the strongest conjugate. So we know our strongest, right, is CN minus. It's going to be the very last one over here. The one that's the weakest is going to have the strongest conjugate.
The lower value of K has the stronger
So as they
base.
get bigger, as the
Let me get one question at a time here. Okay, hang on. Tyler, go ahead, Tyler.
Stronger, like the lower the number,
Weaker the acid.
the weaker the acid.
Right.
So therefore, it gives better base.
That's right. It would have a stronger base. Okay, so the weaker the acid, the stronger its conjugate base. All right, Javante, did that clear that up? Okay, Jamari? Okay, good. All right, so if we look at, so basically you're just going back up the chart, okay? And notice over here on the side it says increasing acid strength. If you wanted to do this like this, this would be increasing base strength. Okay. So then we can see, oh, F minus is going to be next in our line, and then NO2 minus would be next. Let me show you what I'm talking about when I say, uh-oh, remind me later. There we go. Okay, so we have F minus is weaker than NO2 minus, which is weaker than CN minus. Do y'all agree with that? Everybody agree? Okay. All right. Awesome. And so that's the way you just do bases. You just need to know that concept. The weaker the acid, the stronger its conjugate. Okay? The stronger the acid, the weaker its conjugate. All right. Let's look at the next exercise. Okay. So now we're going to start calculating hydroxide and hydronium ions based on our KW value. All right, so we got that KW value a few minutes ago, and it says calculate the H plus or the OH minus as required at each of the following solutions at 25 degrees Celsius. So there's a reason they gave us that 25 degrees Celsius, because KW is 1.0 times, very good, Javante, 1.0 times 10 to the negative 14. Okay, and then state whether the solution is acidic, basic, or neutral. Well, here's what we know so far. KW is the combination of the hydrogen ion times the hydroxide ion, right? And if this number is 1.0 times 10 to the negative 14, and we plug in our other species in here that we know, then we can solve for the one we don't know. But I'll show you the easiest way to do this, because all your front numbers, by the way, this is called a mantissa. Whenever you're dealing with that, that number happens to be 1, okay? And so really all you have to do, if you're just going to subtract your exponents there, all right? So if this one, you're moving this over here and dividing it, and if let me go ahead and do that. So we're dividing 1.0 times 10 to the negative 5th. Okay, so when we deal with exponents, and we divide, we're subtracting our exponents. So we have a negative 14 minus a negative 5th, okay, which is going to basically be a negative 14 plus 5. And so what is that going to give us? A negative 9. And so our hydrogen ion concentration is equal to 1.0 times 10 to the negative 9. It's...
and then we base it off the pH.
Yeah, now it's asking, yes, very good. And so is it acidic, basic, or neutral? Now, which one's bigger, the hydroxide or the hydronium in this case? Because our hydronium, H plus, was 1.0 times 10 to the negative 9. So who wins that competition there? The hydroxide, this one's bigger, and so that means solution A would be basic. Good. Okay. All right. Now, can you do that without doing all that long math?
Yeah.
Okay, so what is the hydronium ion concentration of the next one?
It's
1.0 times 10 to the negative 7. Okay, so that one would be neutral. Yes, Tyler?
H not, more basic than OH.
Which one's the bigger number on A?
I thought the bigger the number, the more acidic.
The bigger the number. Well, it depends on which one's bigger. So is it bigger hydroxide or is the hydronium bigger?
The hydroxide.
The hydroxide's bigger.
Yes.
So go back.
Would be acid.
So go back to this. Let's get all the way back here to this one. Okay. So which one? You said the hydroxide was bigger, right? If hydroxide is bigger than the hydronium, then it's a basic solution. No, it's all good. Okay. All right. So I think we've established that B is neutral, right? Because they're the same. Okay, how about C? Now this one's a little, oh my gosh, what do we have to work it out? Okay, now we know that our KW value has to be times 10 to the negative 14th. I'm just going to erase these in here so we can just do the same thing in here. Okay, so this is OH minus we're looking for, and this number is 10.0. Now, technically, what we could do to make this way easier is couldn't we put 10 in scientific notation? Yeah. So what is 10 in scientific notation? It's 1.0 times 10 to the positive or negative 1? Positive 1, isn't it? Positive 1. Okay, so then we're still going to divide by 1.0 times 10 to the 1. And so we've got a negative 14 minus 1, not a negative 1. And so what's that going to make our exponent then? Negative 15. That's right. Okay, so our OH minus is equal to 1.0 times 10 to the negative 15. And I'm leaving off my big M behind those. Molarity. Okay, so who's bigger?
the
Hydronium, and so this is going to be acidic. Good. Okay, awesome. All right.
I thought that when I was looking at it, but I
Gotcha. Good. All right, let's look at the next exercise here. Do y'all need some more practice on that?
No, I did.
Are you sure? Okay. All right. This is our lecture guide, and I believe I've got on today's homework assignment, I've got practice on this for you to make sure that you're cool with that in your head. Okay. All right. So let's look at sample exercise 4, autoionization of water. Okay. So look at what's going on with the KW. What is happening to it? Is it getting bigger or smaller? It's getting bigger. Okay. So it gets bigger. And what happened to our temperature? Our temperature went up or down from its normal. It went up. Okay. So as temperature goes up, our KW gets bigger. What does that mean? If KW gets bigger, does that mean that these values got bigger? How would we get a bigger? It does mean that. Okay, so that means that that got bigger. And of course that got bigger, the same amount. Okay, so if we're using Le Chatelier's principle, and let's think about, we're shifting our reaction to the right, correct? Everybody with me on that? That means that we're shifting this way. So the question is this an endothermic or exothermic reaction? Endothermic, very good, because heat would have to be on this side, and when we increase heat, that would shift the reaction to the product side. Okay, so that's how you know that. It's all about shifting from left to right. So this is definitely an endothermic reaction, endo. Okay, now our job is to calculate the hydronium and hydroxide in a neutral solution, but we're at 60 degrees Celsius. So we know our KW is 1.0 or just 1 times 10 to the negative 13th. And our expression is H3O plus times OH minus 1.0 times 10 to the negative 13th. It's, but look, Tyler, what we're doing, we changed the temperature. Yeah, it's all good. Okay, now, are these two numbers going to be the same value? Oh, do they have the same ratio in terms of like, look at your balanced equation? Yeah. Weren't they the same value a few minutes ago? Like whenever we didn't have both of them? Let's go back and look at that. Nope, I missed it. Yeah. So back to this. Remember I said that each one of these was the same number in pure water, right? Okay, now when we don't have pure water, that's when we've added some stuff to it, and that can change the ratio of those. But we've got pure water in this one, so they're going to be the same. So what would you call each one of those if we're trying to solve for them? X, and I would call that one an X, and so that would basically just be X squared, right? Okay, all right, so we would need to take the square root of that number, and so you guys have a calculator, so let's figure out what X is. I like you up here. I can see if you're dozing or not. Okay, and that would be the molarity of both the hydronium and the hydroxide ion. Okay, good. I mean, hey, what if you got, let me ask y'all this question. What if you didn't have a calculator and so you got this answer? Is that the same number? It should be, shouldn't it? Because all I did, I took the square root, right? What's the square root of 1? 1, and if you're taking the square root, you're just halving that exponent. So I half that exponent, and that would be 6.5. So you could try it out in your calculator. If you punch that in your calculator and hit enter, you should get that. Try it just to see. So I'm just showing you a way. It's like, oh my gosh, I didn't know how to put that in my calculator. I don't know, just some random reason. It's the same number. Is it the same number? Yeah, okay. Okay.
Right.
It's just cleaned up. It's a cleaned up version. Like this, the number you got in your calculator. It's like, oh, when do we have an exponent that's got a decimal point in it? Yeah, just a cleaned up version. All right, let's move on. Okay, so today in your practice work, you're going to be calculating pH and POH for weak and strong acids, I think. I think we're going to get to that point. All right, so we're going to start with strong stuff, though. And on this, all we have to do is calculate the pH and POH for these. So what exactly is that? So let's go ahead and write down our equations. And by the way, they are on your equation sheet, okay? So if you're like, I can't remember the pH formula, there is no excuse for that. They're on your equation sheet. Just find them, okay? There you go. pH and POH. I'm going to write them bigger so you can see that. All right, the pH equation is equal to the negative log of the hydrogen or the hydronium ion concentration, okay? Now, hopefully you guys are beyond the fear of logarithms. Logarithms aren't hard. They're just an exponent, right? That's all they are. Exactly. Natural log is actually more complicated, but yeah, log base 10 is not a big deal. It's just your exponent. Okay, now POH, we treat that one the same. It's just the negative log of the hydroxide ion concentration. That's all it is. Let me get that over so you guys can see that. Okay, Same exact way of finding it. So the little p, and that's a lowercase p, although mine doesn't look like a lowercase p, it should. It stands for the negative log of. That's all that means. Okay, so if we want to take the negative log of these, and you can try them in your calculator, but if your mantissa is 1, then this is going to be your pH. Your exponent will be your pH, okay? Or actually, my bad, because this is the hydroxide ion concentration. So my POH would be a 3, okay? And here's another little piece of information that you need to know. 14 equals pH plus POH, okay? Put that over there.
So POH is 3, then pH would be 11.
There you go. See how easy that is? So POH is 3, pH is 11. Nice. Okay. All right. Now we're looking at B. Okay. If I wrote that number in scientific notation, what would 1 be in scientific notation? 1.0 times 10 to the, am I having to move my decimal point any? No. So times 10 to the 0, right? And so if this is the H plus and I'm looking at pH, my pH would be a 0 and my POH would be a, there you go, 14. Nice. Okay. All right. Now we're on the next one. It looks like we're going to need to use our calculator. Okay. All right. The pH, well, yeah, maybe. It's all right. The pH of human blood was measured and found to be 7.41. In fact, human blood is supposed to stay between, let me make sure. It's a 10-degree range. I believe it's 7.35 to 7.45. Okay. And so if you go above or below that number, then your body can go into shock. It's like a real crucial thing. So your blood pH is serious. You got to have it in that specific range. It's a little bit basic. It's a little bit above 7, so it's a little basic. If you think about what you have in your bloodstream all the time, you have carbon dioxide. And carbon dioxide mixed with water, CO2 plus water, actually makes carbonic acid. Okay, but carbonic acid is a weak acid, and so this stuff literally undergoes this process all the time. H plus HCO3 minus. And remember, weak acids produce conjugates that are stronger than water. There you go. And so here's your conjugate. That conjugate's stronger than water. So can you see why your blood pH is a little bit basic? Yeah, it's because you've got that dissolved in your bloodstream all the time. Okay. Yeah. Yeah. So you have to, and that's also why sometimes like you have to get people's oxygen levels correct it'll level out their pH. Because if they're carbon, we breathe in oxygen, we breathe out carbon dioxide. So if they're not getting in enough oxygen, then they're not going to be metabolizing enough carbon dioxide, and it can totally whack out their pH blood levels. Okay. All right. Do you have a question, Jasmine? Okay. All right. So yeah, it's kind of cool. And people that hyperventilate can mess up their pH blood levels too. So you have to breathe in a paper bag sometimes because you're breathing in more carbon dioxide and you're getting your blood pH back to normal. Because, if you hyperventilate, you kind of start feeling really weird. And I don't know if I've ever hyperventilated, but people they get to a point where they can pass out because their body's kind of starting to go into shock method because they don't have enough CO2 in their blood. All right, so anyway, we've got the pH of blood is 7.41. And so calculating the POH, well, we're going to take 14 minus 7.41, and that'll give us our POH. And so they'll do that math for me real quick. 6.59. Okay, so that's our POH. All right, now we've got to calculate the hydronium and the hydroxide. I'm going to show you a quick and easy way to do this with your calculator. Okay, so if you've got the pH formula and you're going to go backwards with it, and we have pH is 7.41, and that's equal to the negative log of H positive. So how do you move the negative log over here? all you do with your calculator, since we're advantaged to have those, is we hit second log. It's called the anti-log, okay? And so, but we got to do this negative sign here. And so whenever we move this negative sign over, that would be a negative 7.41 is equal to the anti-log. Well, actually, get rid of this. Try again. I'm just going to rearrange. So we take the anti-log of a negative 7.41 would equal our hydrogen ion concentration. Okay? So second log, and then put your little negative in. Kayla, can you run over there and grab me a calculator real quick? I don't have one here. That way I can show it. Yeah, oh, I do have one. Thank you. Okay. And you don't even see that. Probably not. Let's try this. I don't know if I'm all the way bright. This is brightening it up. Well, I was trying to see where you can see the calculator. And say again. Yeah, we could turn on the lights, especially since I'm using this. So, oh, I see the calculator. Oh, there it is. Okay, but Javante, can you maybe turn on the lights? I'm afraid it's gonna. Can you see the calculator? A little bit. And then bring it down. Okay. Oh, that's worse. Oh, the light bar. That might be intelligent. Haha, look at you, Javante. All right, so if I can center it. Oh, goodness. What'd you say, Javante? Is that better? Okay, all right, so what were we doing? Oh, second log. I just wanted to show how we got that. And then we're going to do a negative 7.41. And so that was our pH that we did that to. So what would that number give us? Right, but what is that equal to? Well, we just plugged our pH in. Our pH was 7.1. No, what is that, guys? We took the negative log of that. Let's look. That's our H plus. Right there. Okay, so our value is 3.89. So H plus equals 3.89 times 10 to the negative 8. Now, we can do a couple things here. We could do the same thing if we wanted to. We already have POH. Or we could use our KW equation. Okay, let's go ahead and let's do the anti-log again. So if we want to find hydroxide, which we do, we need to take the anti-log, so second log of a negative, what was our pH value? 6.59. And that gives us 2.57 times 10 to the negative 7th molarity. Okay. All right, let's continue on because we want to get to the pH of weak acids at some point. Okay, so next one it says calculate the pH of this strong acid. Now the cool thing about strong acids is you don't have to do an equilibrium problem because remember the equilibrium lies far, far, far to the right. So it's really essentially not even an equilibrium problem at all. You're dealing with this stuff completely ionizes in water. So whatever the concentration of the acid is also the concentration of the hydronium ion. So I just need to simply take that number and plug it into my pH equation. Okay, so you guys do that real quickly. The pH is equal to the negative log of 0.1. And we could have put that in scientific notation, not even had to use our calculator. So the pH on that first one is just simply 1. All right. Let me show you how to do sig figs with pH. How many sig figs are in this number? 2. Okay. The number of sig figs is how many places you go after your decimal point, because pH is a log, right? And the logarithm is actually not a significant figure. So we're going to go 2 places after our decimal point. My calculator just said 1, so that's going to be a 0, 0. Very good. And there are no units for pH since it's a logarithm. Okay. All right. And now the next one, y'all tell me, what is the pH of this one? We don't even need to put this in our calculator. It's what, Javante? No. Look at your front number is a 1, right? What's your exponent? 10. So your pH is 10.00. There you go. Good. Okay. So strong acids are very easy to do. Let's look at how we would find the pH of a weak acid, okay, because that's actually where we get into equilibrium. All right. The hypochlorite ion is a strong oxidizing agent often found in household bleach and bleaches and disinfectants. It's the active ingredient that forms when swimming pool water is treated with chlorine. In addition to its oxidizing abilities, the hypochlorite ion has a relative high affinity for protons. Now, let's talk about what this means. High affinity for protons. What does that feeling like that means? If you just use context clues. High affinity for protons. High attraction to protons. Nice. Very good. That's exactly what it means. And remember, a proton in acid-base chemistry is a hydrogen ion. Okay? All right, it's a much stronger base than the chloride ion, okay, and forms the weakly acidic hypochlorous acid. So they give us a Ka value right here, okay. They told us all that other information. Great to know, but right now we're looking at what's the problem. What are we trying to figure out? Calculate the pH of a 0.1 molar aqueous solution of hypochlorous acid. All right. So let's go back. What we're going to have to do is we're going to have to go back a couple of pages. And in our notes, we wrote down how to come up with the concentration of H plus or H3O plus. We wrote this down in our notes, correct? Okay. So if we have the Ka value for hypochlorous acid, we could plug that in. Could we not? Could we plug that in? Yeah. Do we have the concentration of our acid? There it is, right there. Well, actually, y'all can't see that. So, yes, we have it. Okay, I circled it, the 0.1. And what we don't have is we don't have those other 2 values. So, basically, what you've got going on here is we've got a rice table problem. So, let's go ahead and let's write our equation for breaking this down, HClO. Break it down, and don't be scared of it. It's just a way of organizing our thoughts here. Okay, what is this going to form? H positive and OCl minus. Good. Okay, so in our rice table, our initial concentration of HOCl is 0.1. We don't know what the concentration of this is, or we'll just say before we dump it in water, it's 0. Okay, and our change, since those are both zeros, this would be a minus X, this would be a plus X, and this would be a plus X. And at equilibrium, this would be 0.100 minus X, this would be X, and this would be X. Go with me on that? Okay, now we had our Ka expression that I just had on the screen a few minutes ago would be equal to the hydrogen ion concentration times OCl minus over HOCl. Notice I'm writing it specifically for this acid. Okay, I'm not writing HA and A minus. I'm not writing it specifically for that. So then we've got 3.5 times 10 to the negative 8 is our K value or Ka value. We have X on top times X over 0.100 minus X. But guys, ladies, let's think about this. We learned something back, it's been a little while, but we've refreshed on it. And if we have our K value and our original concentration are at least, yes, we neglected X, that's right, Jamari, are at least how much do they have to be different than each other? 1,000 times. All right, 1,000 times different than each other. So are these two numbers 1,000 times different than each other? Oh, yeah. Yeah. So we're going to say this really doesn't break apart very much, and its concentration is about 0.100. And so we're going to do what Jamari said. We're going to neglect X. That's just going to make our math way, way easier. Okay? So we're going to multiply across here, and if I multiply that times 0.1, that'll be 3.5. Y'all need to check my math because sometimes my mental math. 0.1 times that would be a -9, I believe. Y'all agree with me? When I just move my decimal place over one more space. -9 is equal to x squared. Going to need to take the square root, and so x is equal to, y'all punch that in your calculator, see what you get. So 5.91 times 10 to the -5th. And x is that number, is it not? It's also the other number, but we're trying to find pH. So the one we care about is the hydrogen ion concentration. So we know that that is equal to this. And now we just need to take the negative log of it to find our pH. .23. I'm with you. 4.23. All right. So is this solution acidic, basic, or neutral? Acidic. Because we're falling below 7, right? So this is definitely an acidic solution. All righty. Okay, so we need to probably do some more of those, I feel like. Yeah, but I mean, it's going to get easier and easier because if you think about it, it's going to be x squared on top divided by your concentration on the bottom equals your Ka, because I think we should be able, just check, can I neglect x? Are you ever going to have to use the quadratic that I've told you? In my 17 years of teaching AP chemistry, I've never seen a student have to use the quadratic equation on an equilibrium problem. And all that time, the people that I've known that teach AP chemistry for longer than I have, they've said they've never had students to have to use the quadratic equation. So you're going to get to neglect x. Okay. All right. Let's start with sample exercise 9. We're going to do the same kind of thing, and then I'll show you how to actually, instead of calculating percent dissociation, let's just find pH of these. Okay. First of all, would you agree that this is a weak acid? It is a weak acid. You got to know your strongs to be able to determine if it's weak or not. Okay, and it's not one of the strongs, so it's got to be a weak. They gave you a Ka value that is much less than 1. There's another way to tell, oh, it's a weak acid, because we have a Ka value, right? All right, so our job now, it says calculate the percent dissociation, but right now I just want us to calculate the pH of these solutions. We've got a 1 molar and a 0.1 molar. Let's see what the difference is in these two. Okay, so let's break them down. We've got H positive plus, very good, Javante, plus C2H3O2. And this is the same for both of them because it's the same acid. We just have different concentrations of each one. Okay, so if we think about our Ka expression, Ka is going to be H plus C2H3O2 minus over HC2H3O2. Okay, and then I'm not even going to build a rice table for this one. Is that okay with you guys? Okay, because honestly, your rice table is just there to help you organize your thoughts. If you need it to help you organize your thoughts and like figure some stuff out, I say it's extremely useful. But you get to a point where you can like start kind of shortcutting a little bit. Never shortcut this. You always need to write your Ka expression. But if you're like so good at equilibrium that you don't have to do a Ross table, then go for it, because you know that the top two numbers are going to be X. Well, first of all, are they? Is this number and your Ka value, are those at least 1,000 times different? They're not. 1,000 times would be 10 to the third, right? Okay, so 1 is times 10 to the 0, and you've got to the negative fifth. So that's that many zeros, 5 zeros different than each other. Okay, so yeah, they're different enough. How about the next one? Is it different enough? Is that at least 1,000 times different? Yeah, that's 4 zeros. So that's 10,000 times different. So we've got enough information here that we can neglect X in both cases. So we're going to neglect X. So 1.8 times 10 to the negative fifth equals X squared over 1. That's the first one. That's A. And then I'm going to go ahead and do B. Well, I've got it. 1.8 times 10 to the negative fifth equals X squared over 0.1. Okay. And so now we multiply across. That's 1.8 times 10 to the negative fifth equals X squared. This one is 1.8 times 10 to the negative 6 equals X squared. You're going to take the square root of both sides. And your X is your hydronium ion concentration, because we need that for pH, or that's just what it's equal to. But the reason I'm making that important is because we're calculating pH here. All right, I'm going to let you guys tell me what the values are for each one of those. Tyler, you got the first one?
No, I already have calculator.
What?
No.
Go get you a calculator, child. You're going to need one. We have you on video here, Tyler.
That's fine.
That's fine.
But it does.
Okay, the first one is 0.004.
Okay, you want to give me one more sig fig there? 2, okay. All right. Okay. All right. Now, this is interesting. Yeah. 0.0013, 0.0042. Okay. Which one of these? Well, they're almost, it's like the one that has more stuff gave us more ions, right? Okay, over here we have fewer ions. So our pH obviously is going to be lower in this one, right? Than this one, not much. So let's go ahead and calculate pH. pH is equal to the negative log of 0.0042. pH is equal to the negative log of 0.0013. Mm-hmm.
2.376.
Let's go 2.38, okay.
And then 2.89.
2.89, and which was what what I said, we should have a lower pH in this one. Now, the reason that this problem is here is because instead of us calculating pH, which is I just wanted you to have an extra practice problem, we're going to take and we're going to do what it says. We're going to now calculate the percent dissociation. So I want to show you something with these two concentrations. All you have to do to calculate percent dissociation is, well, this is how much actually broke apart right here, your X value, and your original value is your total. Okay, so anytime you do a percent, it's always part divided by the total times 100. It's going to give you percent. So same way with percent dissociation. What part dissociated? Right here, your total. This is how much you originally started with. So on this first one on A, I'm going to take 0.0042 divided by 1 times 100, which is basically going to be, I'm just moving my decimal point over 2 spaces, that'd be 0.42%. I'll check my math. Okay, all right. The next one over here, we've got the 0.0013 divided by 0.1, because its original concentration was 0.1 times 100. Okay, so when I divide by a small number, that actually makes that number, I'm really actually multiplying by 10, so that would be 0.013 times 100 would be 1.3. Check my math. Make sure I'm not lying to y'all. I'll seriously check my math, Caleb. Check my math. You got 13%? Okay. Or you got 1.3? Got 1.3? Okay. Because we're doing 0.00. Calculator keeps going off. Okay. And then divided by 0.1, which makes that, move the decimal place over once, and then times 100. And so 1.3%. Okay, I know this is kind of all over the place, but one of the things I want you to look at, here's 1.3, 0.42%. Which one of these concentrations dissociated the most? The more concentrated one or the lesser concentrated one? That's probably not the way to say that. The least concentrated. That's right. Okay. That's kind of the point that this problem was getting at. The less concentrated actually will undergo more dissociation, a greater percentage dissociation. Okay. So it's like, well, I want to get, you know, my pH to go lower. I'm going to keep adding acid. Yeah, it will. But you need to realize that less sometimes is more. It's like not going to go a lot more. Okay. Just because the less concentrated you have something in these acids, then the greater the percent dissociation. Okay, so you might want to, let's write that maybe on the side or something of our lecture guide here, just so we can make a point. Okay, so note, what do we need to learn from this problem? The lower the concentration of a weak acid, the greater the percent dissociation. All right, I've seen that as a multiple choice test question. Hint, hint. I'm just saying that, yeah. It's just a little factoid, okay, that you need to know. All right, we're going to stop there today with that because I want you to have a little bit of time to work on your practice problems or your homework assignment with your teammates or with your classmates if you so desire. Okay, you got everything you wanted there, Alex? Okay, I'm going to go ahead and stop this video. If you are watching this video right now, you need to come by my room if you haven't done so already and get your assignment. All right. Here we go. I think I just ended that meeting. Okay, so we're going to practice on pH. You're getting it? First thing? Are you serious? You got electrochem, didn't you?
Yeah.
Pretty much? Okay.
From what I didn't miss.
From what you did miss? All right. Okay, so guys, this is basically what we went over today. It goes back to conjugate acid, conjugate base. Okay, this is your homework assignment. Do not lose your lecture guide. Your lecture guide we will keep using. Oh, gee. You don't want one, Alec? You sure, Alec? You're good. I give you one, Kayla. All right. Do y'all like this method? Is it more helpful? Do you feel like we can get more covered? I feel like you like this method better.
What's the method exactly?
Just using this technology.
Oh, no.
Is that helpful? Okay, all right. Then I'm gonna have to buy me a dongle because I'm borrowed Miss Reed's. Mine didn't work. Mine is burnt out. Yes, we are. Yes. Oh, they look good. See, you made them all. Yeah, I have 2 people that need to make up this test, so. I'm always the bottom one. It's not, no, I'm not always the bottom one. Hey, you made 100 when you get your. Yeah.
Okay, it actually is HCl. Itself is a strong acid. Yes.
Well, Jenna, you need to come over. Yeah. Listen, let's roll up. Yeah. The 100. The electrochem test.
Oh, yeah, that was easy.
Yeah.
Oh, yeah, that was.
Alex, you should come here.
Right.
Well, actually, I didn't put those grades in the data. I just showed like I could show what the actual these curve percentages was. I just showed what I'm gonna do. So yeah, actually pretty good. And if anybody else you might know, Tyler, did you come over and see yours? You're on the wall. Yeah, after you do your test corrections. Probably because I need to grade them.
Because I have it for like
Yeah, I need to grade them. I got to finish grading it. Yeah. So,
Number one is
here it is.
concentrated.
What are you looking at? Oh, we're looking at
HCl
that.
is strong. It's concentrated.
So, when is HCl strong? Is HCl strong acid?
Yes.
Okay, so always. So it's always strong.
You know, it's weak whenever.
It's never weak.
I thought when it hits water.
It's never weak. No. Hydrochloric acid is never weak. Now, can it be?
So it's just basically.
It's not a trick question. It's just trying to make you think, So hydrochloric acid is always strong. So there would be always. Weak, never. Concentrated. When would it be concentrated?
Okay.
So this is just making sure you understand the difference in the terms there. Okay. Concentrated just simply means you've got more of it in solution. So if you've got,
I didn't know how you won that like question answer.
Gotcha.
You get on my nerves.
Okay. So concentrated is, let's say, I'm not sure if you guys can see this. Ooh, just made a mess with that. Never mind. Try that again.
Oh.
Yeah, I know. All right. So, it's a good way of showing that. Now I have a nice little. Okay, Jamari, you're giving a good example back there. So if your pee looks like that, oh, that's you, Jenna? Okay, then that means you have concentrated urine, okay? If you pee and it looks like water, that's dilute, right? Okay, so, yeah, and you're dehydrated if it looks like that. That is true. There is some medicine that you can take that makes your pee look like that too. But if you're not taking any medicine and your urine is that dark, you need to drink some water. So, Tyler, to answer your question, I think that could have answered your question versus concentrated versus dilute. Concentrated means that it doesn't have much water, right? And dilute means you have a lot of water. Okay?
Hey.
I didn't mean for it to turn out like that, but yeah. All right, I thought I ended the video. I didn't end the meeting. I'm still sitting here talking to these poor people.
I'm pretty sure. I was recording.
Well, I keep hitting end meeting and it's not ending the meeting.
Stop video.
Pause.
Stop recording. Yeah.
All right. Y'all can't see this part. See where it says end meeting?
Yeah, but it's not highlighted.
Oh, okay. So stop video.
There you go.
At least stop the video. But I
Stop
need to.
Video is where you take